Let me ask you this. Have you ever been out to a movie with a significant other, a parent, somebody you have known for a really long time? And you're watching the movie, and you see on the screen this actor, and you ask, well, who is that actor? And you turn around, and they say to you, oh, he was in that movie we saw that one time. Now, this is a completely content-free sentence, right? So it's first, right? But there's actually a lot of structure in that. Because there's this movie you're watching, there's this actor you're talking about. There's some other movie that he was once in that you went to see with this other person. So part of what makes graphs interesting is we naturally think in terms of connections. And there's so many different verticals in which this makes a lot of sense in computer science and all the things we do in our day jobs, like social networking. Alice is friends with Bob. Computer networking, we keep track of all the different computers, we keep track of build targets, we keep track of dependency graphs, all sorts of things like that. Chemistry, biology, there's so many different other avenues that this can actually be really useful. But today, of course, we construct our data in tables. And for a second, I want you to think about the biggest SQL query you've ever written. Because it probably involves a whole bunch of join tables, a whole bunch of grid statements here to figure out exactly how this works. And what's funny is when you're actually talking about a many-to-many relationship, as for a join table, you're actually talking about a graph. And it turns out that you can actually prove this. Tables are graphs. Graphs are tables. Everything you can represent in one, you can represent in the other. Shout out to some category theory students out of MIT who are really into this and know a lot about how ontologies and knowledge representation go. So the question is, we're all gophers. We write microservices, why not have both? Why can't we also talk about our data stores, key-value stores, SQL tables, so on, as graphs as well? Can we import a paradigm? Can we compile in the ability to talk in this way about these problems? So, a little bit of history on Cayley, not too much, was that about 5 years ago, there was a company called MetaWeb that got bought by Google. And they got knowledge graph working at Google and Google search. But before they were acquired, they were Freebase. And Freebase was a graph database, kind of like a Wikipedia for the world's information. And GraphD was our proprietary engine behind that I helped work on actually while I was there. And it was really kind of cool. So when Freebase was going to shut down, because we had been completely consumed by Google, we were giving our data back to the community through Wikidata, open sourcing some tools like Google Refine and so on. But not GraphD, partly because. So why not GraphD? Well, GraphD was cool. It was written in C99, had a bunch of cool things, been running in production for a long time. Replication, whole 9 yards. But it was also really kind of full of technical debt. It was written in C99. It is human and friendly query language. If I showed you an example, you wouldn't be able to read it because it was all parsed by computers. And custom everything, like our own session libraries, our own thing wrappers around ePOL. It was really kind of nuts. So I took the idea and I said, let's open source the novel parts of GraphD. What was really interesting about it? And we're going to use Go as our standard library because it works really well. And make sure we can at least scale to about what GraphD was while we were a startup, which is 385 million triples. So and also to promote graphs in general, be agnostic into the future, new query languages, new data stores that come out, and make sure we can plug all these things together. So let's dive in. I was asked to do a nuts and bolts talk, so let's actually make this a real technical talk. Here's our example that we're going to be running with. Alice is friends with Bob, and Dave is friends with Bob. We want to know Bob's friends. Seems really straightforward, and obviously it can get way more complicated as things go on. But let's keep it down to this simple graph right here. It is a graph, it's just very simple. And so the Bob file, this is actually the data format you can pass it, is just these two lines. Alice is friends with Bob, Dave is friends with Bob. And what this is that there's a subject, Alice, some predicate, which is the connection node between these two things, and Bob is our target object. Why they're quads, why there's a fourth field that's optional and hidden, that's, that's topics that I probably don't have enough time for. But let's just go with, Alice is friends with Bob, Dave is friends with Bob. These are positions in the triple or the quad. And let's go on. So here's what a graph query looks like, at least for Cayley, which is, if you can write jQuery, you can sort of understand this. Starting from everything, tagging that with friends, so I want to get all the friends, and then follow out the relationships of this friends with and find something that I know to be wrong, is in fact wrong, as opposed to all their friends, if I didn't constrain that. And so the input should look like this, which is tag the vertices of friend, get the results out with the tag filled in, and that's what it should look like. So how does this happen? Here's the life of a graph. This is how we go from query text, parse it, abstract syntax tree, iterator trees, backgrounds, tag paths, result formats, so the results you actually see. And I'm going to talk through this for our time with this. This is also where the code lives. If you're really into Cayley, you want to check out more about how the architecture works. Those folders are actually quite accurate. Let's see. So query languages. We'll start right in. The role of this is to really be a parser. The gremlin we saw earlier is actually just a JavaScript environment using a nice library called auto. I don't know if you're going to use that. Create a user session, store the user session, validate the tree, and return the results in JSON. Pretty straightforward. So the interface primarily for this session object, so parse it, see if I have more I need to get, like an unclosed parenthesis or something. If I am complete or if it's an error, I can tell that the result. Execute it, getting my results back on the channel. And then format those results that I get back on the channel in some meaningful way to have whoever's consuming them. And so, what its goal is to create an abstract iterator tree in the first stage. And that's kind of what this is going to happen here. The input looks like this, the output looks like this. And you're asking, oh, okay, that's a pretty big tree, let's take it a second. Because the next step is abstract iterators. This is what that tree actually means, and let's talk about what they are. So abstract iterators are really just placeholders for sets. They're unevaluated sets. They're sets that represent some amount of data that is yet to exist, and could materialize at all, but it's about to be evaluated. They represent either nodes or links, and we want to be able to have very precise operations on them. If you know set theory, set operations are kind of an important thing here, and of course, and also it's abstract because it is not tied to any particular backend. Because if you remember, we want it to be a microservice. We want it to be an API for graphs on top of any backend we like. So we have to be independent of that and just also hold tags, know how to deal with results, and return them back to the user. So a quick glossary of what sorts of operations you can do with iterators. You can do an intersection iterator, which takes two iterators or multiple iterators and finds the ones that exist in all of them. Or as a union, so just run through them each once, find all of them, combine them all into one. A fixed iterator, which is, hey, I gave you this node to begin with. Here it is, I told you what it is. So just return it for me. That's a really simple iterator, but very straightforward. All is everything in the database at all. Things like this. But in order to do graphs, so those are all very set-based. In order to make graphs kind of work, we really care about the kind of two major iterators, which are links to and has to. Links to says, I have this set of nodes, give me the links to those nodes. I have this set of links, what field do they have such that they are a set of nodes. And with this, we can sort of walk back and forth, get all the quads with the nodes, get all the nodes with the quads, and make a traversal along the path. And as we make the traversal along the path, we can therefore represent this entire set, this query, this tree, without fully evaluating it again. And when we do want to evaluate it, we can do that. So back to the example. We have the all iterator, right? As for starting with everything, tag with friend. Follow the relationship is friends with out. So I gotta find all the links, get all the links that have that relationship type, and intersect them to find those relationships for those people, and then go back down the housing. Is friends with, you'll notice, is a fixed iterator behind, because I told you what it is, it's friends with. And it then gets the links involved. And so then all of it's friends with again, and we might want to make sure at the very end that it's intersected with a set of Bob. We know that this set will evaluate to some huge set of people, perhaps, all of Alice's friends, all of Dave's friends. And then Bob is our target, so we want to convert that and go that direction. How are iterators used? What does the interface look like for this? Well, result is just what am I pointing at? Give me the result. Next advances the set. And next path is a little bit more curious because while next advances the set, there may be multiple ways to get to a target. Right? There may be multiple paths that get me to this element of my set. So how do I know or enumerate those? Let's play a next path. Contains is just, does this value exist within the set? Tell me true. So one thing that's really kind of tricky about it, and I'll come back to this again later too, is that we want to avoid the naive path in evaluating these things. Because this path, right, is to ask for all the people in the world, find all their friends, and just check to see if they're Bob. This is equivalent of going around the audience and saying, are you friends with Bob? Are you friends with Bob? Are you friends with Bob? And you just get a lot of no's. But if we go the way around and say, hey Bob, who are your friends in the audience? You'd say, oh yeah, that's right. But if Bob were, say, on a plane, say it was really expensive to talk to Bob, if you couldn't get to him right now, it could take hours before he lands on his transcontinental flight, it actually might be faster to evaluate the query by asking every person in the audience. So making that decision, making a cost decision, is how you avoid the naive path. However, we're lucky because we already know who Bob is, we already have all the data in our system, so we can next out of the easy part, which is just say the next element must be Bob because he's part of the set. And find anything, and then check to see if any of the rest of the unevaluated query contains this person, or it would contain this person if I evaluated that set. So then we can run that, tag the results. Every node has a result, which is Bob is the top level result. The link that got you there, Alice is friends with Bob, is the link in between that satisfies each of these situations. Is friends with satisfies the fixed is friends with. Alice is the one who is something in the system, it's anything, so that makes sense. And there's our first result that satisfies. Next path, then we can call next path and find other friends. Because that set of Bob is not going to change. We need to actually find the other paths that got us to Bob. So when we call next path, has it can find another link that comes to Bob, checks to see if that link is valid. Sure enough it is, matches his friends with Dave, and there's our other path that gets us to Dave. And then by this, we've just kind of iterated through all the things that get us from some arbitrary friend to Bob. So let's talk about quad stores and concrete backends. There are a bunch of backends that are supported with Cayley. You can write more, they're actually fairly straightforward. This is one. We're right now at the part where we're talking to database directly. This is where we translate and store the data. We translate quad operations to a particular backend that they're talking to. We can pass it, these abstract iterators are passing around opaque identifiers that just have to equal something. So we can translate those to actually meaningful things by asking the database. We can also optimize the query based on what we know the database can do. So if it has a special index or if it has something particular to get that it can do well, we can optimize that case. Most translation in this case then happens in the backend iterators. So you can imagine having a backend iterator which just runs an SQL query, right, for the entire tree. That would work, and that would be some potential optimization for that particular backend. But we want to abstract it in general and then make it more specific. So the primary interface for quad stores is something like this. Obviously these are more fleshed out. I didn't have the full space on the slide to fill it up. But quad iterators give me all quads with this value in this particular field. Nodes all iterators just to give me everything. Optimize iterators, opportunity for the backend to replace iterators. And then translate these opaque values from, here's a string, give me the opaque value, give me the opaque value from the string, so on. So the goal of the database is to ask, what can I replace? And it goes around checking each of the different places from the bottom up. So first thing that a very common optimization would be to look like this. Hey, there's a links to predicate where there's only one thing underneath it. I have an index for that, so I can replace that with my own index. And then I look around again and see, oh, hey, there's this links to and has a, where one of my things is an index I've already built. I know an index for that one, so I can replace that one with a reversal index, and sure enough, we get a concrete iterator tree. Much easier to validate, much faster, based on the backend in particular, and on we go. is because we're coming back around the other side now. We can tag the paths and format the results. So we run it, tag the paths, give Bob and Alice, tag the paths, run next path, tag Bob and Dave. These are the results that come back on the channel. And then we format the output to JSON, and we're back again to the query parsing line part, and we give that back to the user. And we've just gone through the entire scheme of how we go from giving a query to getting the output back again. So one thing I wanted to talk about a little bit was some of the trickier parts of the code base. What's really interesting, and what was the hard part, right? So one dragon was the and iterator optimize. I talked a bit about cost choices, where you could choose to just talk to Bob or ask everybody in the audience, depending on what it would cost. Making that decision and keep composing, changing iterators, materializing iterators, that all happens in and iterator optimize, which is a really tricky bit of code, which I liked writing, which was fun, but it was also tricky. Let's see. Next contains has iterators are the only place where if you want to check if something contains it, you might have another path. It's for real. So because of that, this is where next path comes in, and I'm keeping track of, keeping the bookkeeping of what have I already seen that points into me, what I haven't seen, that's kind of where that dragon lies. It's a little bit subtle. It's not too complicated, but it's subtle enough that I have a number of bugs in that one. Build iterator helper. This one is from the query language, where I'm given this JavaScript object thing, and I need to evaluate it into a Go object. So I'm running through a huge select statement based on, well, okay, what parts of the query line did you give me, and therefore build the appropriate iterator tree recursively. And so that's a huge function that I should really pare down one step at a time. And so, where does this all go? This is some of the feature work. What kind of cool things can you do in the future with databases? Like parallel queries. We could evaluate multiple branches, materialize them into reasonable things. That'd be good. We can have perfect set sizes. This is something I've been thinking about, which is, what if I knew the cost very exactly? Because I know when I'm talking about friendship relationships, most people have, say, 20 friends, 100 friends. Or when I'm talking about classifications, I know that songs tend to have 2 genres. Or maybe I'm talking about any number of things. But knowing based on the schema, I can tell you much more accurately what that potential set size is, and therefore guess at the cost evaluation much more accurately. That'd be cool. New query languages. Last week, if you were reading the tech news, Facebook was talking about GraphQL. That's totally related because they're asking about how can I get this structure, users, names, friends, and give you back the same structure based on what might be linked together. It'd be a really interesting project to implement a GraphQL endpoint. But Sparkle is also one I haven't gotten to, but that's kind of standard for RDF. That'd be a nice one. And optional type safety. What if I told you that an age, the person has an age is a node, that age must be an integer. And if that age must be an integer, I could actually tie that data on top of the predicate itself. Because predicates are just nodes. So maybe he's friends with the expected person, maybe all these things. And then the metadata around the predicates themselves is self-described in the graph using the graph, which is a little bit, disappearing up, one's own eyeballs, I guess, but yeah. And of course, there's many other useful things. Having a Cassandra backend, which I've gotten out and ready to review if somebody wants to take a look at it. Full text indexing, various cool iterators you can do, more replication things. If people really want to go after NP-hard problems, how do you shard a graph or a sharding database? That'd be really a fun project. And in general, graphs provide just this is kind of my closing slide, is graph provide a really cool framework by which you can talk about your data. You can, algorithmically, try and figure out what groups interact with each other. This is, Les Miserables and all the different characters involved. And you can also look at your data kind of as this, thing, right? So there's a tool by which you can look at graphs, there's tools by which you look at tables already. Why don't we have both? Why can't we have sort of an API that's off any key value in SQL is what you like, and file that into our system. So yeah, that's my did for the quick overview. I'm Cayley, and I'll take a whole bunch of questions now because I love questions. That's not good, right?
Do you have any plans to implement graph algorithms such as show us a path between two nodes?
Plans to optimize.
Some of the other databases out there have a number of those.
Sure, I'm sure some other databases still have them. And it would be relatively straightforward to implement. You can do it today using the JavaScript interpreter, but by making that into totally easy, actually. Because now I have all these tools which I can say, give me the list of adjacencies, right? That's a quad in there. So building a Dijkstra's algorithm across, say, finding a short path, finding whatever, it's just a library call away. So yeah, writing the library is easy and I should get it, basically.
Hi, thanks. It was a really good talk. Can Cayley represent sort of a quality hierarchy? So, for instance, in the database word name, you can say that one word is another type of word, like this is a verb, or this is a noun, or something like that. Can Cayley represent that?
Yes, absolutely. Having, say, multiple parts of speech, and even like verbs, transitive verbs, and transitive verbs, you could say, right? These subclasses that also form a greater tree. And one thing you can do is instead of just passing in a single predicate, you can say a set of predicates defined by some other word. You can do a whole bunch of crazy things like that with graphs, which I love that question. It's very fun. So yeah.
Cool, thanks.
Totally.